Swayam Prabha. Digital India. Educated India.
Welcome to this session on electron beam machining and ion beam machining under the course Advanced Manufacturing Processes. In the previous sessions, we have discussed about the electro discharge machining process, electrochemical machining process, laser beam machining processes and some variants of these processes in details. Let us move ahead and discuss some more interesting processes like EBM and IBM, that is electron beam machining and ion beam machining. These two processes are basically used for precision machining of materials or components and considered to be highly precise and costly processes. Electron beam machining, this was first reported by Steigert in 1947, who designed a prototype of this particular machine. Since the year 1960, it is being used in industries for nuclear and aerospace welding applications. However, modern applications of electron beam machining include drilling of small holes, as I have already indicated. Basically, it is used for precision machining of components, then precision cutting, engraving and heat treatment, etc. This process also finds applications mostly in semiconductor manufacturing as well as micro machining areas. The main components of this electron beam machining setup is shown in the following figure. This is basically housed in a vacuum chamber and the vacuum is maintained approximately at about 10 to the power minus 4 torr. This is a schematic of this process. So, this is the vacuum chamber we were talking about, this is in the screen we can see, and this is the cathode from which electrons will be emitted and this beam of electrons will be accelerated towards the other end, in which the workpiece will be mounted. This beam of electrons will hit the workpiece and the workpiece will get heated and the material gets melted and evaporated. There will be other arrangements like, since there is a cathode, there will be an anode owing to which these electrons coming out of the cathode will be attracted towards this anode. However, there will be some other arrangement of accelerating these electrons, and instead of these electrons getting accumulated on the anode, they will be directed towards the workpiece, which we can say the focusing of the electron beams by means of some magnetic lenses, as shown here. These are the pairs of magnetic lenses. So, they will be so adjusted that this electron beam will be focused at a point where the workpiece will be kept. Thus, because of the focusing of this highly accelerated electron beam, so this intense heat will be generated where the electrons will be striking the workpiece and this workpiece will get melted. The only critical thing here is the maintenance of vacuum. A high vacuum to the tune of approximately 10 to the power minus 4 torr should be maintained, and that is why this entire chamber is connected to a vacuum pump, and this vacuum can be monitored to maintain at a particular level. In this setup, a tungsten filament cathode is heated to about 2500 to 3000 degrees Celsius in order to emit electrons. The effect is measured by the emission current, which is of 20 to 100 milliampere in magnitude, and its density is between 5 to 15 amperes per centimeter squared. Emission current depends on the electrode material, temperature and high voltage, that is usually about 150 kilovolt. Such a high voltage accelerates a stream of electrons in the directions of the workpiece. These electrons are focused by the field and travel through a hole in the anode. This generation of electron beam can be explained like this. Say for example, this is the cathode which is connected to the negative end of the power supply, and there is an anode. However, the peculiarity of this anode here is that this is having a hole, and this is connected to the positive end of the power supply, okay. And this therefore, this is something around 15 kilovolt will be applied between this cathode, this is the cathode and this is the anode. Because of this application of this high voltage, there will be stream of electrons coming out from this cathode and will move towards this anode. However, there will be a system of electromagnetic lenses placed on the part of this moving electrons in such a way that these electrons will be focused, or rather this beam of electrons will be focused at a particular point. So, this is the, we can say, the focal point, and this is achieved by this pair of electromagnets, or we can say lens system. They are acting as the lens for the beam of electrons, like the optical lenses used for optical signals. Now, these electrons, if we allow them to fall on a material which is nothing but our work material, then this intense heat of this electrons generated due to the heating of the high velocity electrons on this workpiece surface will cause the material to melt here. So, the melting of the material will take place locally on this portion, and then subsequent heating of this electron beams onto this same workpiece, then this material will come out as the evaporated material, and the ultimate result will be, we will get a sort of curve or a machined portion on this work material. So, this we call as the machined material. So, this is the basic principle involved in electron beam machining. The electron beam is refocused by a magnetic or electronic lens system, so that the beam is directed under control towards the workpiece. The kinetic energy of the electrons is then rapidly transmitted into heat, causing a corresponding rapid increase in temperature of the workpiece, which causes material removal by evaporation. With the power densities of 1.55 megawatt per millimeter square, virtually all engineering materials can be machined by this process. The mechanism of penetration of electron beam in the work material and its material removal is yet to be understood well. It is believed that the workpiece surface is melted by a combination of electron pressure and surface tension. The melted liquid is rapidly ejected and vaporized, as we have already indicated. It causes the material removal in a range of about 10 millimeter cube per minute. The absence of mechanical contact and the suitability of automatic control enhance the process capabilities of this electron beam machining process. However, the necessity to work in a vacuum system increases the cycle time. Comparatively, large depth to width ratios, which is something around 100:1, with applications in fine hole drilling, are feasible in this process. Now, if we define the following terms like ZE is the hole depth removed per pulse in millimeter, then Z is the depth of hole or slot required in millimeter, Fp is the frequency of pulses per second, then Tp and Ti are the pulse time and pulse intervals in microseconds, then the number of pulses required, that is NE, to remove a hole of depth Z can be described by NE equal to Z by ZE. The machining time Tm correspondingly is given by Tm is equal to Ne by Fp, where Fp is nothing but 1 upon Tp plus Ti. Hence, the drilling rate phi in millimeter per minute can be calculated by phi equal to Z times Fp by Ne. According to Kaczmarek, the number of pulses Ne can be described as a function of the accelerating voltage V alpha and the emission current I e. This is given by Ne equal to 1 upon k times I e into V alpha. Hence, phi in millimeter per minute and the volumetric removal rate VRR become phi is equal to k times Z times Fb into I e into V alpha, whereas VRR is expressed as pi by 4 into k times dB square into Z into Fb into I e into V alpha. This is shown in the screen, where this dB is nothing but the beam diameter in contact with the workpiece, or it can be also considered as the slot width in terms of millimeter. Then V alpha is the beam accelerating voltage, which is expressed in kilovolt. IE is the beam emission current, which is expressed in milliampere, and K is a constant, where alpha is the slot length. In case of slotting a depth Z and length L, the slotting time Tm can be expressed as Ne into L by Fb into dB. Then again the slotting rate eta in millimeter per minute can be expressed as K times dB times Fp times I times V alpha, while the volumetric removal rate in millimeter cube per minute can be expressed as VRR equal to K times dB squared Z into Fp into I into V alpha. The depth of penetration of the electron beam depends on the beam diameter, power density and accelerating voltage. This we have already seen in terms of the mathematical expressions. The depth of eroded material per pulse, on the other hand, depends on the density of the workpiece material as well as on the beam diameter. For a fixed set of process conditions, the number of pulses required increases hyperbolically as the depth of the hole increases. Thus, when a certain depth has been reached, any further electron beam machining to deepen the hole would require a very large increase in the number of pulses. Now, let us see the factors that affect the electron beam machining performance. These factors are generally grouped into these subheadings as shown in the screen. These are work material based parameters, in which thermal properties of the material, thickness of the work material, and then type of the work material, whether the work material is of ceramic or superalloy etc., that influences the material removal rate, because the thermal property, since we have already indicated this EBM is a thermal based process, where the material removal does take place because of the melting and evaporation of the work material, owing to the change in the kinetic energy into thermal energy. Therefore, the thermal properties of the material, how fast the material can acquire heat or get heated, depends on will affect the material removal rate or the performance of the process. Similarly, as the type of material changes, like ceramics, they have got different thermal properties, and superalloys, they have got again different thermal properties. Therefore, the time required to get these materials heated and evaporated will be vastly different, and therefore, corresponding performance of the electron beam machining will be different for different materials. Similarly, another very important group of parameters are the electrical parameters, that is voltage and current, and again the type of cathode that we are using, because in this particular machining the performance of the system depends on the emission of the electron, and this emission of electron will highly dependent on the cathode properties. Also, the different materials will affect the life of the cathode. Thus, the cathode property ultimately influences the performance of this process. Similarly, other parameters related to power, applied power are current, voltage and beam cross section. As we have already discussed, very high voltage to the tune of 150 kilovolt are being applied between the anode and the cathode, which causes the electrons to get emitted. Then the other parameters are time based parameters, that is removal per pulse and the frequency, and then electron beam pulse, that is duration of the pulse, energy per pulse, frequency and the acceleration voltage applied. This acceleration voltage is another very important parameter, as we have already indicated, discussed earlier. This acceleration voltage will be responsible for providing the kinetic energy to the electrons and the focusing of the beam onto the workpiece. So, these parameters ultimately affect the material removal rate, surface quality, accuracy, etc., in electron beam machining process. Now, let us see the applications, common applications of this particular process. Basically, this process is useful for precision drilling applications. Generally, it is suited for drilling of small holes up to 1.5 millimeter diameter, and the depth wise it can go up to 10 millimeter or so. For increased depth, however, it requires stable power supply. With increased control, drills up to 19 mm have been reported. The inclined holes can also be drilled by this electron beam machining process. Perforation of thin sheets can be easily carried out using this EBM. Foil made of synthetic material has been perforated with 620 holes per square millimeter for filter application at a rate of 1 hole every 10 microsecond. This talks about the precision we can have with this particular process. In 1 millimeter 620 holes can be drilled, which is very high as far as the precision of the process is concerned. Thus, a large number of holes per second can be drilled very economically. Another application is slotting. Regular slots of 0.2 by 6.35 inches in 1.6 millimeter thick stainless steel can be produced in 5 minutes using 140 kilovolt 120 microampere current with a pulse width of 80 microsecond and a frequency of 50 hertz. This has been reported by researchers. Rate of slotting depends on, of course, the work thickness. 0.05 millimeter stainless steel can be cut at the rate of 100 meter per minute, while 0.18 millimeter thick sheet can be cut at the rate of 50 meter per minute with similar machining conditions. Thus, we have seen as the thickness increases, the rate of machining comes down significantly. The EBM process is suitably used in fabrication of integrated circuits or IC technology. Other applications of this process include production of filters and masks of color television tubes, for manufacturing sieves in sound insulation, glass fiber productions, etc. Then let us note few disadvantages of this process also. As I have indicated at the very beginning, the equipment cost for this process is very high. The production time also relatively longer. This is basically primarily because of the vacuum generation time. as we have already indicated, vacuums to the tune of 10 to the power minus 4 torrs are required for effective machining to take place. Then as we have indicated, this is a thermal based process. So, there will be a thin recast layers as well. Then it may need auxiliary backing materials for machining to be performed. Now, let us move on to another precision beam machining technique, that is plasma beam machining. In plasma beam machining, the gas temperature is raised to about 2000 degree Celsius. The gas molecules get dissociated into separate atoms. At high temperatures of 30,000 degrees Celsius, these atoms get ionized and the gas is called as plasma. In the year 1950s, plasma was adopted as an alternate to oxy-gas flame cutting of stainless steel, aluminum and other non-ferrous metals. Recently, it is being used for both ferrous as well as non-ferrous metals. The working speed and cutting rate is much faster in plasma beam machining and the curve produced is also much lower. It is very popular for machining stainless steel. In plasma beam machining, a hot tungsten cathode and a water cooled copper anode are used to produce a continuous arc. The gas temperatures of around 28,000 degrees Celsius are enough to produce a high temperature plasma arc. In this process, the material is machined by melting and evaporation. The general characteristics of plasma beam machining are indicated in this table. In this process, velocity of plasma jet is something around 500 meter per second. Then material removal rate can be obtained in 150 centimeter square cube per minute. Then specific energy is 100 watt per centimeter cube per minute. Then power range is between 2 to 200 kilowatt. Then voltage applied is 30 to 250 volt. Current is very high, it could be up to 600 ampere and machining speed could be 0.1 to 7.5 meter per minute and maximum plate thickness that can be machined could be 200 millimeter. Different types of plasmas are used for machining systems such as plasma arc, plasma jet, shielded plasma and air plasma. Material removal rate in plasma beam machining is attributed to the plasma torch which blows away the molten and evaporated metal as a fine spray or vapor. Machining speeds of up to 5 times more than oxy-gas cutting can be obtained. In fact, this is being reported by different researchers. The machining speed is found to decrease with the thickness of the metal or the cutting width. Let us see the accuracy and surface quality that can be obtained in plasma beam machining. Edges cut by plasma beam machining are often having small wevels due to clockwise swirling of the machining gas. The depth of fused metal extends up to 0.2 millimeter below the metal surface. The distortions in the cut materials are little due to high machining speeds. Since this process is also a thermal based process, a heat affected zone up to a thickness of 0.25 to 1.2 millimeter are reported. clean smooth surfaces are produced in plasma with very few micro cracks below the heat affected zone. Materials can generally be cut within a tolerance rate of plus minus 1.6 millimeter. Let us quickly look at the advantages of this process. The plasma beam machining processes does not require any complicated chemical analysis or maintenance. The process uses no harmful chemicals or acids. Operation is clean and eliminates further cleaning that is required, such as vapor degreasing, blasting and solvent cleanings. Thus, as such the operation is clean. There are few disadvantages as well. The first one is the large power is required for cutting. For example, a power of 220 kilowatt may be required to cut a 12 millimeter MS plate, mild steel plate at 2.5 meter per minute, which is quite high. Process generates large heat that can spoil the workpiece if not properly controlled. The process may also produce some toxic fumes. Now, let us look at the applications of this process. Plasma arc machining, attractive turning method for difficult to machine materials by conventional methods. Cutting speeds of 2 meter per minute and a feed rate of 5 millimeter per revolution with a surface finish of 0.5 millimeter RT are reported. Computer numerical controlled plasma beam machining is used for profile cutting of metals that are difficult to tackle by oxyacetylene gas, for example, stainless steel and aluminum. Plasma beam machining is used to cut grooves in stainless steel. The process is also recommended for parts that have subsequent welding operations. Underwater numerical control plasma are also used with higher machining accuracies of plus minus 0.2 millimeter in 9 meter at a lower cutting speed. Now, let us move on to another precision beam machining technique, that is ion beam machining. In short, it is known as IBM. The ion beam machining is carried out in a vacuum chamber using charged ions fired from an ion source towards a workpiece by means of an accelerating voltage. The mechanism of material removal in this process differs from those in EBM and PBM, that is electron beam machining and plasma beam machining. In ion beam machining, the atoms are ejected from the surface by other ionized atoms which bombard the work material. Accordingly, this process is also known as ion etching, ion milling or ion polishing. Now, let us look at the ion beam machining system. The system consists of an ion source that produces sufficient intense beam of ions for removal of atoms from the work surface by impingement of ions. A heated tungsten filament acts as the cathode from which the electrons are accelerated by means of a high voltage, which is around 1 kilovolt towards the anode. This figure shows this process in which this the schematic is in the screen, in which this is the cathode which will be responsible for emitting the electrons, and there will be some intermediate electrodes, and of course, there will be an anode to which these electrons will be attracted. However, there will be controlling electrodes which will guide these electrons, speeding electrons towards the workpiece, and these will hit the workpiece at a particular point, in which instead of heating mechanism, the atoms will be removed or ejected because of the heating of the atoms or ions on this workpiece. Therefore, this is rather than thermal process in which melting and evaporation does take place in case of electron beam machining and plasma beam machining. Here atoms will be removed or ejected out because of the heating of these ions on this workpiece surface. As we have already indicated, the process also needs high vacuum, and therefore, the entire chamber will be connected to a vacuum pump. There will be again electrostatic lens systems, which will in fact guide or control the beam of this ions onto the workpiece. During the passage of these electrons from the cathode towards the anode, they interact with argon atoms in the plasma source to produce the argon ions. A magnetic field is produced between the cathode and the anode, which makes the electrons spiral. The produced ions are then extracted from the plasma towards the workpiece, which is mounted on a water cooled table. So, this can be explained like this. In this process, again there will be a cathode. So, this is C is cathode, and there will be an anode system, say anode system, which will be connected to the anode of the power supply. So, this will be the power, and therefore, the electrons will be attracted towards this anode. This is anode. Now, in between there will be argon gases we can say. So, this is AR gas, and this argon gas will be ionized by this high moving electrons, and the argon ions will be, now these argon ions will be focused or accelerated towards a particular point or a focal point, which is nothing but the surface of the workpiece material. So, this is nothing but the workpiece material. This is done by a special mechanism of fields, or we can say electrostatic fields. This is electrostatic field for controlling the beam of ions. Thus, this beam of, when this beam of ions hit this workpiece surface, atoms of the small atoms of this surface will come out from this surface, workpiece surface. Therefore, these are ejected, we can say these are ejected atoms rather than the evaporated materials as in the case of PAM or EBM. So, these are nothing but ejected atoms, and this will ultimately cause the machining of the workpiece material, where the beam exactly hit the material, workpiece material. So, this will look like this. This is also called etching. The machining variables which can be independently controlled are the acceleration voltage, flux and angle of incidence. Let us look at the material removal rate in this process. Once the ions strike the machined surface obliquely, the atom ejection occurs due to the collision. The sputtering yield, that is the number of atoms yielded per incident ion, are higher for oblique cutting than normal incidence. The material is removed by transfer of momentum from the incident ions to the atoms on the surface of the material. The atoms removed from the surface are deflected away from the material. Energies greater than binding energy of 5 to 10 electron volt are needed to effect the removal of atoms. At higher energies, sufficient momentum causes removal of several atoms from the surface. The yield and hence the machining rate depends on the binding energy of atoms in the material being machined. It also varies due to the introduction of gases. The each rate V theta in atoms per minute is given by, as can be seen in the screen, 9.6 into 10 to the power 25 s theta into cos theta divided by n, where s theta is nothing but the yield in terms of atoms per ion and small n is the target material density, which is atoms per centimeter cube. Then let us see about the accuracy and the surface effects of this ion beam machining. Machining of small dimensions as 10 to 100 nanometer are possible using this ion beam machining. Accuracy levels of plus minus 1% with repeatability of plus minus 1% have been reported. Smoothing to a surface finish of less than 1 micrometer can be obtained. Let us look at the applications of this process. The IBM process is used in smoothing of laser mirrors as well as reducing the thickness of thin films without affecting the surface finish. In this regard, thinning of samples of silicon to a thickness of 10 to 15 micrometer have been reported using argon ions impinging at normal incidence by Magog in the year 1988. Using two opposing beams, samples for transmission electron microscopy can be produced. This is a very critical application because the sample preparation for transmission electron microscope is a critical job which needs very thin samples to be prepared. Polishing and shaping of optical surfaces by direct sputtering of preforms in glass, silica and diamond can be performed using patterning masks. The process can produce closely packed textured cones in different materials including copper, nickel, stainless steel, gold and silver. Atomically clean surfaces can be produced by IBM process that are used in addition of gold films to silicon and aluminum oxide substrates. Layers of surface oxide can be removed by using higher ion energies. Ion beam machining can mill a line width of 0.2 micrometer, which is used in fabrication of bubble memory devices, of depth to width ratios of 2:1. Now, let us summarize what we have discussed in this session. In this session, we have discussed 3 more advanced manufacturing processes, namely electron beam machining, plasma beam machining and ion beam machining. The principles of operations of each processes have been discussed, the setups have been discussed, and some unique advantages and limitations as well as applications of all the 3 processes have also been discussed. We hope the session was informative and interesting. Thank you.